The title is that one, and deals with the non-proportional loading. And we have heard during the whole day about several problems, mainly in this morning, about the non-proportionality of the loading. Anyway, so just to give an idea, I will talk about this kind of non-proportionality. So usually in our tests, non-proportionality is the combination of two proportional loading with a kind of out of phase, or in any case, two proportional case with an independent time history. This is one possible definition. I have to say that I don't want to address or to tackle this general complexity. The aim of this paper is, when I have a specific problem with a given property, is it possible to have a shortcut for a given problem? Because to deal with the overall complexity of the non-proportionality is really complex. So, which is our problem? Let us start from the problem. That's our problem. So we deal with high cycle fatigue of an hydraulic press for ceramic tiles, and which is the main property of the structural behavior of this machine. This is a preloaded structure. So we have a particular out-of-phase loading or non-proportional loading that is the superposition of one static load plus one or a couple or three time variable independent loading. So in the material we have one static, the stress tensor variable in time, we have one static component plus one, let us start with one time variable component. I will call this simplified non-proportionality. So, another point is, I said that I don't want to tackle with the general problem. So, which is our material? Our material is a ferritic ductile cast iron. And we had the multiaxial fatigue test, and as known in literature, this material is dependent on the principle of stress variation. And in particular, this material has a clear dependency on the mean value. So the mean value of stress has a great influence on the fatigue stress. Here we have data, experimental data. This is not uniaxial. This is a summary of several kinds of multi-axial tests with different degrees of biaxiality and even considering out-of-phase loading. And we can summarize with a kind of very simple equivalent stress. So the critical plane is the plane where we have the highest combination of the normal stress amplitude plus a part of the mean value, and the constant B is obviously dependent on material. So, which is the problem? The problem is that this component is very complex. So we have so many geometrical details, so many potential critical points, very complex finite element models, even if we want to do a kind of parametric optimization, something like that, we have a very heavy problem. So our aim is to develop a fast algorithm for critical plane assessment. I'm not saying that the algorithm already available does not work. I'm looking for something specific for this application, but somehow faster. Because we know that often the available algorithms are numerical, somehow iterative or recursive. Is there a possibility to have one explicit solution, for instance? So, this is our loading. A static tensor plus a pulsating set. So, varying from 0 to 1 of another independent component. So, we can write the normal tensile stress. And it is in this shape. And to deal with this problem is quite easy. We can write the mean value, the amplitude, and if you simply look at the amplitude, we find a trivial result, because we find that the maximum stress amplitude is the maximum eigenvalue of only the time variable part of the loading history. So we can write something like that. We can find with an eigenvalue analysis directly the amplitude and the direction. But this is not really the problem. The problem is to address the equivalent amplitude, not simply the amplitude. But from mathematical point of view, the approach is the same. We are simply to write now the resulting value, that is a function of the tensor. We can then compute the maximum value, and it turns out that the maximum value of the equivalent amplitude is the maximum eigenvalue of two possible tensor, which is the combination of the time variable one, the constant one, depending on the property of the material. And so we have this kind of formula. Is it possible? An example. If, for instance, we have a static torsion plus a time variable tension, we can address this problem with this tensor is a static one, this is the time variable, and the result is that the equivalent amplitude depends on both. Obviously, for this material under this condition. And this is true and has been verified because actually this material has an influence of the mean value or the static value of the torsion loading on experimental test. But at this point, I can tell you even in a short way. So I can add as many independent time variable components as you want. They simply have to be independent. What does it mean? If I have one loading and then it go back to 0, then I have another one, I can analyze with this procedure this kind of loading. Because if the time variable components are independent, I can simply focus on the extreme and to check the combination of each extreme. So I have to check what happens from here to here, for so time 1 versus time 2, but is similar to the previous one. So I already solved that. The same from T3 to T4. The problem is, can I address what happens between T2 and T4? Yes, it's a little bit more complex, but it's possible. The approach is actually the same. If you want, we can discuss it in the details. anyway, is in any case a combination of available tensors. And I can go directly to summarize the result. I have the possible amplitude that is out from the comparison of time 2 versus time 4, then time 1 versus 2, and time 1 versus 4. This is a set of possible equivalent stress amplitude, which is the actual I'm looking for, obviously the maximum. So, actual equivalent stress amplitude is the maximum value of these possible, the maximum value of the eigenvalues of these tensors. I don't know if you agree with me that it's much more simple than it could appear, but it's really simple because, as a matter of fact, with this approach, you can address a fatigue problem with the investigation of 6 fictitious static loading. That is, these 6 cases. And the highest principal stress of these fictitious static cases is actually the amplitude, the equivalent amplitude we are looking for. So, the advantage of this approach is that under this condition, we can compute directly or address a fatigue problem with the conventional finite element model, simply defining fictitious loading. And obviously, let's say we have done it, and we have done it in the components, just to give an idea, and we have single load cases. We combine with this approach, and we can define. I wrote, I didn't tell, we are dealing with a high cycle fatigue strength, so we can somehow define simply a kind of safety factor, comparing the equivalent value with the reference strength, and to depict the safety factor all over the component, because this computation can be easily done at each node of the finite element component. So, even go to the conclusion. So, our aim was to tackle a specific problem that I don't know if is, let us say, a unique case. In my opinion, and in our opinion, it could be, this case could appear each time there is a preloaded structure with one or a couple of external loads. It is possible to have this case. In this case, in our opinion, it's possible to find the critical direction, even if the loading is actually not proportional. It's possible to find the critical direction in a very fast and simple way, according to the definition of, let us say, fictitious static loading. And the critical direction are the principal direction of the fictitious loading.